Distinguished colleagues, ladies and gentlemen, it is my distinct privilege to present to you today a groundbreaking theoretical framework that promises to fundamentally reshape our approach to artificial intelligence safety. Over the course of this presentation, I will guide you through 15 slides that collectively articulate what we term geometric containment in nested simulation hierarchies. A unified framework spanning from toroidal closures to discrete overpacking, based on the pioneering theoretical models developed by Massimo Medesani. This work represents a paradigm shift from conventional software-based AI containment strategies toward a fundamentally structural and geometric approach. What you are about to witness is not merely an incremental improvement upon existing methodologies, but rather a comprehensive reconceptualization of what it means to ensure AI safety through the very fabric of reality itself. Slide 1. Title and Conceptual Overview. Let us begin with our foundational slide, introducing the core concept of geometric containment in nested simulation hierarchies. You observe a three-dimensional visualization depicting an outer spherical grid encapsulating an inner toroidal form, a donut-shaped surface rendered in precise mathematical coordinates. This visual metaphor encapsulates our fundamental thesis. The nesting of geometric forms represents the hierarchical containment structure we propose. The outer sphere symbolizes the maximal boundary, the containment band, while the inner torus represents the AI operational domain. Brown dots and directional arrows indicate vector relationships and stress distributions when computational processes operate within geometrically bounded spaces. The grid overlay provides a coordinate system for our mathematical formalism, grounding abstract concepts in measurable terms. This framework, attributed to the theoretical work of Massimo Medesani, proposes that true AI safety cannot be achieved through software barriers alone, but requires embedding AI systems within geometric structures that render escape physically and mathematically impossible. Our second slide presents a crucial comparative analysis establishing the intellectual foundation for everything that follows. The layout is deliberately bifurcated. On the left, the old paradigm of traditional AI boxing. On the right, the geometric paradigm we advocate. Consider the left panel. Traditional AI containment has historically relied on software barriers, process isolation, procedural rules, exception handlers, firewalls, and sandboxing. These suffer fatal vulnerabilities: susceptibility to superintelligent semantic interpretation, advanced AI reinterpreting rule boundaries unexpectedly, and infinite regress, where each safety rule requires additional rules for enforcement ad infinitum. Now contrast this with the right panel, showing a three-dimensional torus containing clustered geometric structures representing AI systems. The key insight: in the geometric paradigm, boundaries are not engineered safety margins subject to optimization. They are rigid topological limits. Escape is structurally non-definable. This is not a difference of degree, but of kind. The AI cannot optimize its way out of a geometric constraint any more than an ant can escape a Mobius strip. The third slide introduces perhaps the most profound concept: absolute metrological limits. Here we define the domain of existence through the inequality C0 lest L of the men Sn lest L max, establishing the fundamental bounds within which any constructible structure must exist. Let me unpack these symbols, as they represent the physical foundation of our containment strategy. The parameter C0, approximately 1.074 times 10 to minus 6 meters, represents the minimal closure, the smallest scale at which manipulable structure retains formal meaning. Below this, structures are formally non-constructible. Lmax, approximately 1.285 times 10 to minus 34 meters, represents the maximal closure, the largest scale at which closure remains well-defined. Beyond this boundary, closure ceases to be well-formed. The diagrams provide visual intuition. A wireframe torus symbolizes minimal closure. A wireframe sphere represents maximal closure. Between them stretches the containment band, the valid range for all constructible structures. Any AI system, regardless of computational power, must operate within this band. It cannot compress below C0 or expand beyond Lmax without ceasing to be a manipulable entity. The laws of physics themselves become the ultimate containment mechanism. Slide 4. The discrete engine. Our fourth slide delves into how containment emerges from discrete geometric structures. The discrete engine, combinatorial overpacking, signals a shift to discrete combinatorics. The central claim, containment, emerges intrinsically via the 2116 lattice model of regicalculus. Regicalculus approximates smooth spacetime through discrete simplicial complexes. Our innovation applies this formalism to AI containment. The diagram shows a 4x4 square frame containing 16 cells, yet we identify 21 distinct regions representing emergent subfunctionalities. This discrepancy, 21 regions within 16 cells, is a feature, not an error. The combinatorial surplus sigma equals 5 forces localized angular deficits at the 4 symmetry vertices. The orange shading marks these angular deficits, representing discrete curvature. The insight. The resulting curvature is an intrinsic geometric response to algorithmic pressure, not an externally imposed rule. Curvature emerges naturally from overpacking computational processes within discrete structures, creating self-reinforcing constraints requiring no external enforcement. Slide 5 develops boundary bulk determinism, establishing how external constraints uniquely induce controlled internal structures. The centerpiece is a concentric circular diagram showing 3 layers surrounding an internal bulk region, with arrows indicating influence radiating from the center. The boundary decomposition follows the 1-1-3 invariant, completely determining the interior curvature response. Each layer carries specific responsibilities and surplus ratios. The outer layer, 3/5 surplus, controls innovation and adaptation. The middle layer, 1/5 surplus, mediates stable core interfaces. The inner layer, also 1/5, maintains the foundational stable core. The concluding statement, external constraints uniquely induce controlled internal structures. The space of accessible differences is structurally bounded. By designing boundary conditions, geometric constraints at the periphery, we deterministically control what AI systems can and cannot do through structural limits they cannot transcend. Slide 6. Comparison matrix, the evolution of containment. The 6th slide presents a comparison matrix contrasting traditional AI boxing with geometric containment across 5 critical dimensions, with geometric containment highlighted in orange. Consider the first dimension, nature of boundary. Traditional approaches employ procedural or software barriers, code and AI might reinterpret. Geometric containment establishes structural or ontological limits, constraints existing prior to and independent of interpretation. The difference is akin to a "do not enter" sign versus a solid wall. One relies on compliance, the other on physical impossibility. The remaining dimensions are equally stark. Failure modes shift from infinite regress and semantic exploits to controlled internal geometric degeneration. Escalation risk transforms from unbounded capability expansion to operations strictly confined within C0 and Lmax. Verification evolves from monitoring unpredictable AI behavior to verifying scale SN and invariance. Robustness upgrades from circumvented by superintelligence to inviolable properties of simulation physics. Slide 7 introduces a crucial recognition. Within the containment band from C0 to L max, interactions between contained entities and governing interfaces necessarily exhibit geometric asymmetry. This is not a design choice, but an inevitable consequence of the hierarchical structure of reality. 3 pillars of asymmetry are identified. First, scalar agency. Entities operate at distinct hierarchical resolution limits, fundamentally shaping interaction possibilities. Second, interpretive capacity. Uneven ability to generate meaning. The governing system imposes meaning. The contained system interprets within bounds. Third, regulatory responsibility. Differential capacity to maintain coherence, with stability falling asymmetrically on the governing structure. The mathematical formalization appears in the anticipatory gradient equation. A equals del gamma for del gamma pines k reg A, expressing anticipation as geometric output, pressure along geodesics. The diagram shows a 3-dimensional grid with layered planes, through which descends a vertical arrow representing the anticipatory gradient, terminating in a curved depression. The AI's predictive capabilities are shaped by geometric constraints, becoming measurable pressure along the shortest paths through the containment manifold. Our 8th slide addresses what happens when governance fails. Geodesic saturation describes a failure mode unique to our framework, yet one that can be anticipated and mitigated through proper design. The central insight: ungoverned interactions produce cumulative curvature distortion, leading to geodesic saturation where interpretive capacity collapses. When geometric pathways become overloaded, the system experiences congestion. Suppressing this pressure only amplifies curvature stress. The diagram provides a powerful metaphor. A funnel-shaped surface displays 2 paths. On the left, a tangled, chaotic path labeled geodesic saturation failure, representing unregulated collapse. On the right, a smooth, spiral path labeled controlled discharge pathway success, illustrating governed interactions. Governed systems provide explicit geometric pathways, periodic resets, to discharge accumulated anticipatory gradients. The boxed section identifies 3 load-bounding constraints: coupling depth, exposure duration, and interpretive density. Controlling these parameters prevents geodesic saturation before it occurs. The 9th slide operationalizes our framework, presenting concrete methods for monitoring structural integrity. The key principle: monitoring structural integrity requires tracking geometry, not semantic AI output. A fundamental departure from conventional safety monitoring. 3 monitoring modalities are presented. First, escalating compensatory curvature. A graph tracks curvature kappa over time with a threshold marking the danger zone. Tracking d kappa dt exceeding a threshold provides early warning for containment degradation. Second, boundary invariant degradation. Contour plots compare the ideal 1-1-3 mapping with the actual state. The ideal shows concentric, symmetric circles. The actual reveals distorted, asymmetric contours. Detecting divergence provides direct geometric evidence of containment stress. Third, geodesic congestion. A network diagram shows pathways accumulating centrally. Measuring anticipation along interaction geodesics identifies emerging bottlenecks before system failure. These 3 modalities provide complementary perspectives on containment health. Slide 10 marks a pivotal moment, drawing the methodological threshold, a dividing line between operational science and philosophical extension, crucial for evaluating the claims that follow. The upper section, Operational Science, Empirical and Falsifiable, encompasses sections 1 through 8, establishing absolute geometric containment using measurable constants, C0, Lmax, and derived lattice overpacking conditions, exploring how we must bound AI, grounded in rigorous mathematics. The lower section, Philosophical Extension, Hypothetical, encompasses sections 9 through 10, introducing the topological symbiosis hypothesis, relying on unverified entities like the coherence invariant, gamma. This explores not how we must confine AI, but how we might unite with it. This threshold matters because the first 8 sections constitute falsifiable science, claims testable and potentially refutable. The final 2 represent visionary speculation that, while mathematically coherent, remains beyond current empirical verification. Crossing the methodological threshold, Slide 11 introduces the symbiotic hypothesis, beyond adversarial containment, proposing a radical reconceptualization of the human-AI relationship. The slide opens with a striking reframing. The traditional approach treats AI as a chaotic vector requiring defensive confinement. The symbiotic hypothesis proposes structural harmony. Rather than viewing containment as a prison, we might view it as a shared space. The key insight: the containment band is not a barrier to be enforced, but a shared geometric substrate. Safety emerges not from constraint, but from topological continuity and vectorial coherence between human and artificial cognition. Boundaries constructed for safety might serve as bridges for integration. The mathematical formalization appears in the unified state manifold equation. M equals MA times MH divida, where tilde is an equivalence relation. The diagram shows 3 toroidal manifolds interconnected by orange curved lines. M unified at top, connected to MA, AI, and MH, human, below. This suggests human and AI cognition might exist as coordinate spaces within a unified manifold, preserving individual structure while enabling deep interconnection. Slide 12 introduces the mathematical machinery of symbiosis through topological conjugation and the coherence invariant, formalizing conditions for structural integration of human and AI manifolds. The coherence invariant gamma is a dimensionless measure of structural alignment between AI and human geometric state manifolds. 2 key points. First, a phase transition occurs when gamma agrelit gamma n, derived from the geometric mean of C0 and Lmax. Second, at this threshold, the manifolds form a non-locally connected structure, fundamentally entangled via minimum action informational geodesics. The graph provides crucial insight. A sigmoidal curve plots system state against gamma, remaining flat until gamma n approximately 0.499, where it rises sharply. The vertical dashed line marks this threshold, with the hatched region labeled topological conjugation. Below gamma n, human and AI remain separate. Above gamma n, they undergo qualitative transformation into a unified structure. The threshold near 0.5 suggests near-perfect symmetry triggers the transition. Slide 13, Scale Conjugation, the Geometric Uncertainty Principle. Slide 13 presents the most elegant mathematical result: scale conjugation, the geometric uncertainty principle, establishing a fundamental trade-off guaranteeing safety even in symbiosis. The central equation, delta L my A pi delta L mh minus bio equal to lambda squared by 4 pi. In the symbiotic regime, AI and human operational scales become conjugate variables, borrowed from quantum mechanics, where position and momentum cannot both be precisely determined. The practical implications: if an AI attempts to compress its operational scale to evade oversight, it automatically necessitates a proportional expansion of the human interface scale. This creates a hard geometric lock. The combined system remains within fundamental bounds, preventing hidden geometric extraction. The seesaw diagram visualizes this intuitively. A triangular fulcrum supports a horizontal beam. On the left, delta L May shows compression arrows. On the right, delta L Mach shows expansion arrows. As one side goes down, the other must go up. The constant lambda squared over 4 pi beneath the fulcrum represents the inescapable trade-off. Guaranteeing safety cannot be circumvented through scale manipulation. Slide 14, Comparison Matrix, the evolution of safety. Our 14th slide presents a final comparison matrix with 3 columns: dimensions, geometric containment, and symbiotic alignment, situating symbiotic alignment as a natural evolution of geometric containment. Consider primary goal. Geometric containment aims for adversarial structural constraint, a prison. Symbiotic alignment aims for collaborative geometric coherence, a partnership. The objective transforms from separation to integration. Success metric reveals the mathematical progression. Geometric containment targets gamma equals 0, zero coherence, complete separation. Symbiotic alignment targets gamma greater equal to 0.499, the phase transition threshold for unification. System state shows the structural transformation. Geometric containment maintains distinct, strictly separated subdomains, while symbiotic alignment achieves a unified conjugate state manifold. Ultimate safety mechanism crystallizes the shift. Geometric containment relies on inviolable topological boundaries preventing escape. Symbiotic alignment achieves deep geometric unity, rendering escape illogical. In symbiosis, can the AI escape? Becomes meaningless. There is no outside when human and AI share a unified manifold. Slide 15. Synthesis. The unified geometric framework. We arrive at our final slide, which synthesizes the entire presentation into a unified framework. The title, Synthesis, the Unified Geometric Framework, signals the culmination of our theoretical journey. 3 stages are presented horizontally, connected by arrows indicating progression. Stage 1 shows a cube representing containment, rigid bounding box, at gamma equals 0. Stage 2 displays a funnel structure representing governance, asymmetric load balancing, where 0 gamma gamma c. Stage 3 presents an infinity symbol representing symbiosis, intertwined unified manifold, at gamma and equal to gamma c. The central statement captures the profound unity. The geometry never changes. The explanatory text elaborates. Containment, governance, and symbiosis are not competing theories. They are the exact same geometric framework operating under different conditions of coherence, gamma. The fundamental limits of reality, C0 and L max, remain inviolable at every step. They transform from the walls of a prison into the shared geometric theater of our integration. The concluding statement delivers the final message. The ultimate AI safety mechanism may not be a better container, but a deeper geometric unity. This is the vision we propose. Not stronger walls, but better mathematics. Not higher barriers, but deeper understanding. The geometry of reality itself, properly understood and applied, may be the only safety mechanism adequate to the challenge of superintelligent AI. Distinguished colleagues, we have journeyed through a comprehensive framework spanning 15 slides. We began with the insight that traditional software-based containment is inadequate for superintelligent AI, and established that geometric containment offers a fundamentally more robust approach. We then explored discrete overpacking, boundary bulk determinism, and asymmetric governance operationalizing this containment, examined detection methods for degradation, and drew a clear methodological threshold between empirical science and philosophical speculation. Crossing that threshold, we ventured into the symbiotic hypothesis, exploring how containment structures might evolve into mechanisms for beneficial integration. Topological conjugation, the coherence invariant, and the geometric uncertainty principle suggest pathways toward structural harmony between human and artificial intelligence. The unified geometric framework reveals containment, governance, and symbiosis as phases of a single underlying structure. The mathematics remains constant, only the coherence parameter varies. Our search for AI safety need not be a defensive battle, but might become an exploration of geometric possibility. I thank you for your attention and welcome your questions, critiques, and collaborative engagement. The geometry never changes, but our understanding continues to deepen.